Welcome back to our engineering mechanics lecture, and today we will continue where we left off in the last lecture. Remember, last lecture we talked about centroid locations, and today I want to talk to you about moments of inertia. Moments of inertia is the word that engineers use most often, but scientifically speaking it would be correct to call these second area moments. And just to give you a reference to our last lecture and to exercise your mind a little bit, remember that last lecture we calculated x bar, for example, by the integration or the summation of x tilde I times ai divided by the summation of ai. And why am I telling you this today is because I want to remind you that this portion here, which is an area times the lever arm, we called this the first area moment, and this was the first area moment about the y-axis. And I will talk a little bit about this, about the y-axis in today's lecture, because we will of course take this to the next step now, and we will move from the first area moment to the second area moment. And let me give you a little preview of why it's called that way. So here it's called the first area moment because we have a lever arm times an area. So first area moment because the lever arm or distance. And in this equation up here, it is a linear lever arm. So if this gets longer, the moment linearly increases. And so maybe you can already understand where the second area moment will take us. The second area moment will actually introduce a square here. So we will take the lever arm and multiply it by itself, and then we actually end up with the second area moment. However, I will refer to this as the moment of inertia, or most often I will just in writing say MOI for moment of inertia. But before we talk about the moment of inertia, let's take a look at our objectives today. And let me tell you that the first thing we need to discuss is the material arrangement or the distribution of the geometry within the cross-section. What do I mean by that? I mean that if you have a cross-section that looks like this, right? You have all seen these I-beams before. There's a reason why engineers actually create these cross-sections in such way, or sometimes you have seen, for example, an angle, or sometimes maybe even a tube, and so on. And those cross-section distribution, they have a reason, and that's the first thing I want to talk to you about when we discussed the importance of the material arrangement. And once we have an understanding of that, I would like to talk to you about simple shapes first. So first we need to understand the meaning of simple shapes and the moment of inertia. So what are simple shapes in the context of this lecture? We are talking about shapes that are very well defined in terms of their geometric properties. So let's say a rectangle or a triangle, for example. Those shapes have very known, easy geometric properties, and so I can derive the moment of inertia for those shapes for you. Whereas for these shapes, which are actually composite shapes, so I have, for example, here a rectangle, and a rectangle glued together, that is a little bit more complicated, and that requires actually the parallel axis theorem. So the parallel axis theorem is the next thing I would like to talk to you about. And I need to define that because we want to ultimately talk about composite shapes. So if I want to calculate the moment of inertia for composite shapes, I first have to introduce to you moment of inertia for a simple shape and then the parallel axis theorem, so we can combine such simple shapes into more complicated shapes like these. That will then allow us to ultimately calculate the moment of inertia for composite shapes if we have all our puzzle pieces in place. So our last goal here today is to calculate the moment of inertia for composite shapes.